I'm doing ZF style so that a set has elements. It's built out, iterated out of other elements. It's got lots of other sets. But the point I want to draw, so these might have, one set might have lots of functions to and from another set, but every set has exactly one function to every singleton. So I'm going to draw some fuzz here, because we don't know how many, but there's no fuzz here. We know there's one function from every set to this. We know this one has a unique set to it. We know this one has a unique function. Everything has a unique function to that. This, on the other hand, has a unique function to every other set. The empty set has a unique function to every other set. As to the relations between the others, again, this one, there are as many functions from this set to that as there are elements of that, right? Because this is a singleton. Who knows how many that might be? So I'm going to draw some dots. But there's exactly one function from here to that because that's a singleton. So this has exactly one function to that. Oh, this wasn't meant to be the same letter as that one. So this is some other set. So set looks, it's this vast network of arrows, but I want to pay attention to singleton sets and the empty set. The empty set has exactly one function to every other set, the empty function. Every set has exactly one function to any singleton set. Over here in group, well, a group has to have at least a unit element in it. That might be the only thing. You can have a one-element group, but you can't have an empty group because it has to have an identity element in it. You got lots of other groups, and in a way, this looks a lot like set in that we have no idea how many functions there might be between any two groups, except that we know that this has a unique function, group homomorphism to every other group, because the identity here has to go to the identity there. And since the identity here is all there is, there's exactly one homomorphism. And every group has a unique group homomorphism to it, because you take everything to the identity element. So already we see a difference between the category of sets and the category of groups. The category of sets has an initial element, we call it. It's got a single map to every other element. And it's got terminal elements. A terminal element, everything has exactly one map to it. But they're not the same. The empty set has a map to the singleton, not the other way. No non-empty set has any function to the empty set. In group, we've got a terminal object. It's also initial. In group, the terminal object is also an initial object. So there already at this level, we see a difference between the category of sets and a purely categorical difference between the category of sets and the category of groups. In the finite categories I drew, let's take the richest of them. This element is terminal. Everything has exactly one map to this. I'll say map, arrow. Everything has a unique map to this. It has an initial object. Everything has a unique function from this. Those ones, finite categories, have that. In the singleton category, this object is both terminal and initial. It has exactly one function to every object, because it's the only object there is, and it only has the identity. In the category that I called P, we have an initial object. This object has exactly one arrow to every object. It has the identity to itself, has only this to there and only this there. This has an initial object. It does not have a terminal object. This category has no terminal object and no initial object, because this has two arrows to there, not just one, so it can't be initial. And it's obviously not terminal because this has no arrows to it. This is not terminal because it has two arrows to it, not one, and it's not initial because it has no. So a category might or might not have initial objects, might or might not have terminal objects. Oh, right, I'm using this today. And the last concept I want to introduce to you is the concept of isomorphism. It used to be just obvious to mathematicians that two groups having the same group structure is a different thing from two topological spaces having the same topological structure. I will mention the group of real numbers with addition. Compare the group of positive real numbers, real numbers strictly greater than 0, with multiplication. These two have the same group structure. And there's even a name for that, which is logarithm. Well, exponential in that direction. Exponential, yeah. Exponential in this direction. E to the x plus y is equal to e to the x times e to the y. Taking any number, any real to its exponential, takes addition here to multiplication here. And it has an inverse, the natural log. Because the natural log of e to the x is x. So the reason, the reason logarithms were originally invented was that instead of multiplying positive numbers, once you know their logarithms, you can just add the logarithms. These are two groups with the same group structure. Adding real numbers is really the same thing as multiplying positive real numbers. A modular calculation of logarithm tables. Compare a sphere and a rectangular box. I mean a hollow rectangular box. They're not the same shape, but they have the same topological structure. You could put that sphere around the box and then project every point onto the nearest one of the box. And that's going to, here it's not going to stretch things together. Here's going to bend things a little bit. In some places it will mash them together more, in other places less. But topologically it's not going to change the structure. And on the other hand, you can project out from the box onto the sphere. So I hope you see that topological structure, we don't care about bending and stretching. These two have the same topological structure. It used to be just obvious to mathematicians that sameness of group structure is a different thing from sameness of topological structure. And they had different names. One's about groups, the other's about topology. Groups with the same structure were called holoedric at one point. Two groups are holoedric if they have the same group structure. Topological spaces with the same structure were called homeomorphic. Morphe there means shape, same shape. Topological spaces were called homeomorphic. Andre Weil Sometimes I learn things by being wrong. I once asked Saunders MacLean, would anybody ever have said that Andre Bay was the greatest mathematician in the world? And Saunders said, I don't know who wouldn't. You know? And Saunders worked in a department, let's say. So they said there was great confusion. The very meaning of the word isomorphism varied from one theory to another. Actually, for historians in the room, they didn't even use the word isomorphism. He means what we now express by isomorphism is expressed differently in different theories. They didn't even use the word. Eilenberg MacLean's categorical definition of isomorphism became a standard across mathematics almost immediately after they gave it. They gave a purely categorical description. Here, I talked about exponential function, logarithm. Here, I talked about projecting things in and out. Category theory doesn't have these things. We can get them, but the category axioms don't have it. They gave a purely categorical definition of isomorphism. Today it just means mutually canceling maps in a category. It's the same word for all structures. In any category C, an arrow F from A to B is an isomorphism if there's some arrow G from B to A, so the composite one way is the identity on A, the other is the identity on B. I think, to me, it's easier to see it in a picture. To say that this is an isomorphism means there's some arrow the other way, so the composite is the identity, and having done them in the opposite order, the composite is also the identity. There's some arrow G that exactly undoes F, no matter which one you did first. Do F first, then G, that's the identity on A. F first, then G, identity on A. Do G first, then F, that's the identity on B. An isomorphism is an arrow in a category that has another, then G is called the inverse of F. An isomorphism is any arrow in a category that's got an inverse. I really want to stress this difference. There's nothing going on here like exponential and logarithm. Now here I have shown, take a number, take its exponential, take its logarithm, you get that number. That's like saying, do F first, then G, you get the identity. But over here I don't have a logarithm or exponential. These are just arrows in a category. And also, it is important that e to the natural log of x is also x. So here we have just this quick a definition of isomorphism. In these finite categories, only the identities are isomorphisms. Of course, the identity arrow is always an isomorphism because it undoes itself. That is, it does nothing. So going back here, if F is the identity on A, so if B was the same thing as A, and this is the identity, and that's also the identity, of course they compose to give the identity. Yeah, identity arrows are their own inverses. They're always isomorphisms. But apart from the identities, there are no isomorphisms here. In fact, in these categories, there's no arrows that have another arrow in the opposite direction at all. It just doesn't happen in these. Of course, it does in other finite categories. But in these, there's no isomorphisms here, except the identities. In set, a function is an isomorphism in the categorical sense, if and only if it's a bijection, one-to-one and onto. So it doesn't identify any two different objects, and it covers every object there is. So if and only if the sets have the same cardinality. So a famous example, historically very important, consider the set of natural numbers, where I include 0, 1, 2, 3, 4, the set of all natural numbers. Consider the set of all prime numbers, 2, 3, 5, 7, 11, 13, and so on. There's a bijection. We can take this to the first prime, and this to the next prime, and that to the next prime. We're not going to mash any two things together, and we're not going to run out up here before we finish those. The set of primes is in bijection with the set of natural numbers. This bothered people a lot at one time because they said the primes are a tiny subset of the naturals. How can they be in bijection? Well, they are in bijection. Well, whatever you make of that, they clearly are. Galileo considered this and said, I guess this is a complicated idea, I don't know about it. Georg Cantor looks at it and says, that just means the two sets are the same size. And Cantor turned out to be right. He makes that work. It's the foundation of modern set theory. So if and only if it's a bijection. I said this is wrong. A and B could have the same cardinality without every function between them being bijections. These two sets have the same cardinality. There is a bijection between them. There are lots of bijections between them. But there's also, of course, there's also a lot of functions that aren't bijections. I might mash these three together. Then it won't be a bijection. It's not one-to-one. I might miss this one. It won't be a bijection. It's not one-to. So that second thing, it's not enough that A and B have the same cardinality. It's that F has to be a bijection. Now there exists a bijection if and only if it is, but not every function. In group, a morphism has this property also if and only if it's a bijection. If and only if it's a one-to-one and onto. Because that guarantees they have the same multiplication table, it turns out. We did require they have the same multiplication, but this is enough to guarantee it. But in topological spaces, a bijective continuous function will not be an isomorphism if A has more open sets than B. So for example, I can give you a picture of that. Take the real line, the nice continuous real line. It has a topology. The open sets are like open intervals or unions of open intervals. A set is open if anytime it has a point, it has all the points very near it. Now take the discrete set of real numbers. For every real number, I'm going to put that in there. But I'm going to have it discrete. I'm not going to have them be continuous. Now, the projection there is a bijection. Every real number is up here, and it gets taken down to that real number there. And no two different reals get taken to the same thing. But this space is torn apart more than that one is. These are not topologically isomorphic. You can see this doesn't look like it has the topology of that. This space isn't continuous. It's bijective with the continuous space. It's got the same number of points, but it's got more open sets, because up here every singleton counts as an open set. A singleton here is not an open set. No, it takes a neighborhood to be an open set. So a topological space, the isomorphisms. A continuous function is an isomorphism in the categorical sense if it's bijective, but also open. The inverse image of any open subset has to also be open. I mean, continuity says the inverse image. Openness says the direct image of any open set has to be open. But this is an open set, and its direct image is just that point. And that point is not open. So this categorical notion of isomorphism, it's not the same as bijective. It looks like bijective. It is the same as bijective for sets. In that category, it's the same as bijection. It looks like bijection for groups because if an arrow is a group homomorphism and is bijective, it does have an inverse. And that happens in general algebraic systems. But it's not the same as bijective for topological spaces. And I should say, lots of structures that are used in lots of mathematics and analysis and geometry and number theory are much more complicated than just sets with structures anyway. So that bijective doesn't even make sense for a lot of them. most kinds of structures, the categorical definition agrees with the old traditional sense of sameness. I have to say, actually, for topological spaces, there were a couple of senses of sameness. It agrees with one of them. The categorical definition agrees with one of them. It is a lot more general than the traditional cases, because the category axioms are abstract. It's utterly general. And lots of traditional mathematics, people didn't even have a notion of sameness of structure. Well, we've always got one in category theory. And in every case, the categorical definition is now the standard. If there used to be some part of math where they had a traditional definition of sameness that didn't agree with this one, they've now given it a different name. They don't call it isomorphism. Isomorphism means what it means in category theory. They didn't lose the old definition just for not being isomorphism, but they don't call it sameness of structure. They call it something else. Philosophers of mathematics usually officially define isomorphism as a bijective structure preserving a function. I don't know what happened to this slide. They more or less follow Bourbaki definition. Okay, I know what happened there. I misspelled the word. That's supposed to say definition. There was supposed to be a slide where I distinguished three structuralisms. Besides category theory. Now to your insiders, because you're taking a short course on this, we often call categories cats. It's a natural thing. And besides, cats are nice. So we often say, so besides cat theory, there's traditional vague. Like Riemann. There was a sort of naive, there's topological structures, there's algebraic structures, we know what structures are, we know how to work with them, that existed before Zermelo and Frankel gave you any alternative anyway. So that for these people, structuralism was just obvious. They didn't know any other way you could do math. But it was vague. It did not meet modern standards of rigor, and it was not easy to read. Sometimes philosophers of mathematics will talk about, back in the 19th century when math was concrete and intuitive. They're not reading 19th century math books. Those books are impossible. They were very hard to read. They worked, but they were vague. Then you have Bourbaki. Bourbaki's structure theory. Bourbaki was a group of French mathematicians who got together starting in 1935. And they wrote, I'll put it in English, Elements of Mathematics. And I don't know how many volumes that went to. Multi-volume series, Elements of Mathematics. They rewrote mathematics from the ground up. And they started with a book on set theory and structures. And I misspelled this also, without meaning to, mathematics. That's just supposed to be the word mathematics. They proposed this structure theory. The first sketch came out in 1935. The final version came out in 1957. A lot of philosophers of mathematics know about Bourbaki. They had a huge influence on how math is taught. Mathematics before Bourbaki was taught in terms of problems. They would give you problems in analysis, here's how we solve it. Problems in differential geometry, here's how we solve it. the solution would normally draw on many different techniques. To solve a problem in differential geometry, we would use some differential geometry, some analysis, some algebra, and these would be hard problems if you're talking advanced courses. Bourbaki said, no, we're going to teach methods. We're going to teach you the methods of algebra, then we're going to teach you the methods of analysis, then we're going to teach you the methods of geometry. Hard problems, we actually won't get to that. The hard problems they don't get to. And so a lot of people said, oh, this is terrible because mathematicians aren't learning how to solve hard problems. Well, they did learn how to solve hard problems, just not from this book. This turned out to be the right way to teach math. And this is how math books are all written today. Math book, people don't much read Bourbaki's Elements of Mathematics anymore, and some people say that's because it didn't work. No, it worked so well, math books are all written in a style descended from that. Not the same style, but they utterly changed the style of mathematics books. Everything is now written in a way that descends from this. A lot of it is better than this, because it's been descending for a while. They had a theory of structures. A lot of philosophers of mathematics have been interested in Bourbaki's theory of structures. I will say for the philosophers, and if there are any historians in the room, by 1955, most members of Bourbaki decided that this was just no good. Even before it was published, they decided it just wasn't going to work. And the series never used this. It didn't work. They went ahead and published it because they'd written it, but Bourbaki's theory of structures just never worked, and they never used it themselves. People who talk about it normally haven't read it. People who've read it try to forget. Well, not exactly, but it's hard. It was a great attempt. These are great mathematicians who were interested in logic and foundations and wanted to make this precise. But the way they tried is just, that's hard, and it didn't finally work. And then 3, modern philosophical structuralism. Where philosophers, I've mentioned Banastra, Resnick, Shapiro, Hellman, try to give theories of what structures could be. They've written long theories on this. I didn't mean to say modern philosopher, modern philosophical theories of structure. And philosophers of mathematics who pursue this usually officially define isomorphism as a bijective structure preserving function, more or less following Bourbaki, except the theories they give, they're simpler than Bourbaki's. But remember, Bourbaki's already didn't work. So they're really very far from being able to work. This is the main thing I want to say to philosophers of math. If you want to know, how would you do a subject like Galois theory in Hellman's structuralism? I don't know. You could ask him, he could work on how to do Galois theory in his structuralism. But if you want to know how would you do Galois theory categorically, you can read any book on Galois theory, because it is done categorically. That's how it's done. They officially follow that, which Bourbaki rejected, and actually most of their talk is even vaguer than that. Most of what they say is much vaguer in that they don't specify what structure they're talking about. They don't say what structure is to be preserved. The problem for structuralist philosophers is complex conjugation and isomorphism. And I'll talk about this problem. Tomorrow we'll do functors and natural transformations, including natural isomorphisms, and that will set us up in a position to talk about foundations. Oh no, this is scary advice for me. Does this mean I already knew, or I have found out?
I already knew.
Okay, but it could mean I just found out. Yeah. So I hope everything I'm about to say I already knew and I don't just find it out. Complex numbers are sums a plus bi, where a and b are real numbers, and I squared is equal to minus 1. I hope this is not a brand new idea to anybody. We adjoin a square root of minus 1, a plus bi. They add, in the obvious way, a plus bi together with c plus di. Well, that's a plus c. You just add those. Plus b plus d times I. We add up the real part and the imaginary part. We call this the imaginary unit. We add the real part and the imaginary part. And a plus bi times c plus di. Well, we multiply this by ac plus adi plus, now we'll multiply this by bci plus bdi squared. But that's minus 1. This is minus bd. So it comes to AC minus BD plus AD plus BC times I. So we have addition and multiplication. It turns out this is a field. Any real number has, any complex number that's not 0 has another complex you can multiply and get 1. I won't do the calculation, but it's a straightforward calculation. And the structuralists say, this is an interesting problem for us. Because this equation can't distinguish positive I from negative I. Because these two have the same square. And if our whole definition of I was that the square is minus 1, then how do we know which of these two it is? They're two different things, but they seem to have all the same relations to other elements of the field. What they say is, to put it more technically, complex conjugation which takes a plus bi and maps it over to a minus bi, because we couldn't tell which was I, which was minus I, is an isomorphism. Because obviously, if we do this again, if we conjugate again, we'll get a minus bi. Right. But that's just a plus bi. So this is an isomorphism. It's its own inverse. It undoes itself. So we can't tell a number from its conjugate, because there's an isomorphism that takes one to the other. And any number of philosophy of math books say that complex conjugation is an isomorphism. Indeed, well, let's see, I don't know, I don't want to change how I'm doing this. It is an isomorphism of real algebras. Because in real algebras, the morphism, the structure we're preserving, is the addition and multiplication. We're preserving the algebraic structure. In addition to multiplication, this does preserve addition and it preserves multiplication. It's obvious it preserves addition, and a straightforward calculation shows you it preserves multiplication. So our name for this, if this is alpha, then we call this alpha conjugate. We call this alpha conjugate, and that is just alpha. And it's straightforward to see that given alpha and beta, the conjugate of alpha plus beta is alpha conjugate plus beta conjugate. That's really quick to see. And it's not a lot harder to see that the conjugate of their product is in fact alpha conjugate times beta conjugate. This map preserves addition or multiplication. Certainly 0 conjugate is 0 because there's no imaginary part here. 1 conjugate is 1, again because there's no imaginary part there. Now I conjugate, that's negative I, but that's okay. So this preserves the algebraic structure. It preserves the 0, the 1, addition, and multiplication. This is an isomorphism of real algebras. And that's what the books are all talking about. So they say, no, that's a big problem because if the isomorphism can't distinguish I from negative I, we can't say they're equal. It's obvious that I does not equal negative I because if I equals negative I, then, for example, then I squared would have to equal I times negative I, because if I is negative I, these would have to be equal, but that's equal to negative I squared. If this is equal to minus 1, this would have to be equal to plus 1. So they can't be equal, and yet there's an isomorphism, but they have all the same properties. So how can we be structuralists and talk about them having all the same properties without being equal? Well, we can talk about solutions to that puzzle, but my complaint for right now is that even to say that there's an isomorphism, complex conjugation is isomorphism, is ambiguous. It's an isomorphism of real algebra structure. But remember, for us, isomorphism is inside a category. We can't ask whether this arrow is an isomorphism, because isomorphism is inside a category. In the category of real algebras, this all exists and is an isomorphism. But that's not the only category where it exists. I will do it. It's not an isomorphism in complex analysis. It's not an isomorphism in the category of analytic spaces, because it doesn't have what's called a complex derivative. There's another context where we're not interested in just preserving addition and multiplication. There's another context where we say an arrow has to have a derivative. This thing doesn't have a complex derivative. So, just the working answer in mathematics, I once had a mathematician ask me, is the complex conjugation is an isomorphism? He was testing me. Conjugation, complex conjugation, it takes the complex numbers to the complex numbers. A plus bi goes to A minus bi. Is an isomorphism in the category of real algebras. Running a little low there. Is not a morphism at all in the category of analytic spaces. And for us, isomorphism is always inside a category. We can't, for mathematicians and especially for category theorists. When you talk about the complex numbers, did you mean the complex numbers as a real algebra or the complex numbers as an analytic space? They are both. Galois theory, using complex numbers algebraically, an extremely important part of math. Complex analysis, using complex numbers analytically, also a real important part of math, actually slightly older than Galois theory, and probably bigger today. But they use different categories, and so different notions of isomorphism. This puzzle is complex conjugation and isomorphism. So many philosophy of math books say, yeah, here's this thing, it's this isomorphism, and how do we understand it? To a modern mathematician, it just depends who you're talking to. If you're talking to an algebraist and you say complex conjugation is an isomorphism, they won't skip a beat. They'll say, sure. But if you're talking to an analyst and you say complex conjugation is an isomorphism, they'll say, what? No, conjugation, that's not an analytic map at all. So here, I think that the categorical perspective says, look, there's no one answer to that question. It depends where you ask it. Working mathematician's perspective also says there's no one question. It depends where you ask it. For us, it depends which category you ask it in. For the mathematicians, it depends which office in the math department you ask it in. So this is, I think that I would like to see philosophy of mathematics take what's actually going on today in mathematics more seriously. For tomorrow...
Before you is there a typo word, the morphism or isomorphism?
Oh, it's not a morphism at all. Yeah, it's not just that it doesn't have an inverse, it's not a morphism. That's a habit that I think some category theorists have that might not be super useful, and I should probably try to get rid of it. I will often talk indifferently about arrows, morphisms, maps. I will use all of these to mean the same thing. Now, all of these are in a category C. You can only talk about these if you're inside some category, because then you know what the arrows are, the morphisms, the maps. But I will use these three words probably too interchangeably. Yeah. So it's not an isomorphism in complex analysis. It's actually not a morphism at all, right? So what I wrote here is different from there. What I wrote here is stronger. It's not a morphism at all, and also true. But remember, our whole strategy is we don't want to talk about groups without talking about them in the category of groups. So we can talk about morphisms between them, isomorphisms of them. We don't want to talk about topological spaces without talking about them in the category of topological spaces. Now we're talking about all these categories. Wouldn't we like to talk about them with some notion of morphism? Yes. Morphisms of categories are called functors. We'll have a functor F that goes from a category C to another category D. And what category C is some cloud of arrows, and maybe some of these arrows compose and have that as composite. And category D is some other cloud of arrows that might look quite different. But then these are going to have to compose. A functor is going to take every arrow here to one there. Maybe, here's a good time to use a different color. We'll take this arrow, say, we'll take it to that one. And we'll take this arrow. Now it does have to go to some arrow that starts where this one ends. And in this case, there's only one. So we're going to have to take it to there. We'll take this arrow. Oh, this is the composite of those. So we're going to have to take it there. But this arrow might go to that one. This arrow might also go to that one. It's some way of depicting this network of arrows, but it does have the property that connected sequences here go to connected sequences, maybe mashing some things down to identities. Commutative triangles go to commutative triangles. That's going to be functors. And so now we have a category of categories and functors. Foundational problem, right? It can't be a category in the same sense. It can't be the category of all categories or normal foundations any more than you can have a set of all sets or normal foundations. Now, you can have a category of all categories on, say, new foundation set theory, but it works better. It works better. So we'll get that, and then we will come to natural transformations. Once we've got this idea, now shouldn't we be able to compare one functor to another functor? We better be able to, because that's how we always like to do things. These things are going to be called natural transformations, and as I think I put in the abstract, I will explain to you what's natural about them. This functor is a picture of this network over here. This functor is a different picture of the network over here. A natural transformation takes this picture and sort of flows it onto that picture. We're going to take one picture and we're going to move it onto the other picture. That will be a natural transformation. Exactly how it works, well, I will explain. In logical order, natural transformations are the most complicated thing here. But in the history of category theory itself and in the history of mathematics, the natural transformations are really what it's all about. They're actually the most natural, most obvious part. Eilenberg and McLean discovered natural transformations before they had categories or functors. They defined functors to try to explain what natural transformations could be. And then they defined categories to explain what functors could be. But in logical order, we'll get to that last. Okay, well, thank you. Oh yeah, other questions. Have you got a question? Well, maybe people would want to discuss individually.
Yeah, that's fine. Also, I can send you. Please.
Can we have slides?
Oh yeah.
I'll send them around.
Yeah.
I have a small question. Is the identity morphism unique on every category by definition or?
Well, the identity morphism is on each object of a category. Each object has a unique identity morphism. Now each category also has a unique identity functor. And each functor has a unique identity natural transformation.
So they are by definition unique, right?
Well, no, it's not by definition, it's by axiom. Because, remember, the identity on A has the property that when you compose it with any F that you could compose it with, you get F. So if you had a different identity on A, where composing that with any G also gave you G, now what's this identity composed with this identity? Well, on one hand, it has to be that identity because of the identity property here. And it has to be the other identity because of the identity property here. So it actually follows from the identity property that there can only be one. The same as in groups, but not in some other related structure.
So, other questions? Maybe I have one.
Yeah.
Very general one. So, could you show us an example which cannot be taken as a category. So everything can be.
Well, I mean,
Yeah, like
now measurable, generalized functions on the line. Well, they're not really functions. They don't take the line to something else. So they don't really fit into the category very so well. You can do generalized function theory in a categorical way, but the generalized functions won't be arrows of a category because they don't really compose with each other. So there's things like that, you know. But there aren't things that are commonly considered structures that can't be handled this way. One thing, there are things where you might really, instead of thinking of it as a category, you might want to think of it as a functor. You've got the same objects, but you've got more arrows here, and you mesh some of them together down here. So you really want to think of it as two categories. That kind of thing happens also.
So if you want to ask some private question, you can talk to Colin later on. But also, I will send out sort of a questionnaire, and you can leave anonymous comments again on this 问卷星. So then you can leave your name, but also you can just don't leave your name. So if you have any comments or questions, you can just right there. Yeah, I will send around the questions.
I'm very interested to see if you have any.
Yeah. Nice. So see you tomorrow.
I know